OX2 Solution Private Limited, Faridabad, India. Before that, he has worked as a business analyst at Icon Solution Private Limited, Mumbai, India. He also worked as a programmer analyst in Cognizant. He has developed some of his achievements. There are many achievements, but I'll give some of his achievements. He has developed an image classification system, batch and web application in Python for classifying real estate image using CAF and neural networks. He has also developed a web scraping system to generate relevant tag information for web kiosk application in a predefined format. He has also developed a dashboard to showcase the performance of builders, communities, homes as per location. How do they fare among their competitors, and also to predict performance stats for next few months. So I'll stop here and I'll give this virtual lecture to Vaibhav Goel. Sir, over to you, Vaibhav Goel.
Thanks for the introduction. So I have with me, I have my team here, like some of the members from the team, Anurag Banerjee, Kashif, and Akshay Kalra, who will be assisting, like we all will be helping each other in this workshop. So we'll be mainly talking about the things which we do with computer vision at our company, and some of the stuff which we have been doing in the past. A brief disclaimer before this session, before we start, is like the content which we have used is all from the web. We do not endorse any brand name which we have used within this whole PPT or workshop, and this is mainly for the academic purpose. And here we haven't disclosed anything which is IP within the whole, like within EX square. Like we have just disclosed whatever is there on the web, and we have tried to structure in this whole thing in such a way that you can all understand, and it may get you started for doing something within the field of computer vision. So I'll share my screen to start with the PPT. Before that, I'll tell you a brief about my team as well. Sorry, skip that part. So Kashif has been working with us for more than 3 years. He has pretty strong hold on computer vision and NLP tasks. Same goes for Akshay and Anurag. They both joined us 2 years back, and I can surely say everybody is awesome within the team. So I'll share my screen to get started. So how we'll go about is like we'll be showing a PPT. We'll be talking about some of the things which are done within this industry, and then we'll show you some live examples, like how things are done really. Right. So here goes the screen. Sorry, just move to the part. Is my screen visible?
Yes, it's visible.
Okay, so usually, like whenever we talk about computer vision, one thing which comes within the mind is like what it is. So basically, like whatever we see from our eyes, be it images, be it videos, be it something else which our eyes can see and analyze, that comes under computer vision. So this is a classic definition which comes from the IBM. And here, like we can also say in such a way, like when we were as a kid, we didn't know anything about any of the things which we see in this whole world. As in when we were told about some of those things by our family members, we got to learn them, whether this is a tree or a dog or a cat or something else. So say, in a similar fashion, things are done within the field of computer vision, where we share some of the attributes or some data to let them know, like an X object or an X image or an X view is a cat or a dog or something else. And in a similar fashion, the whole neural network works in terms of learning and predicting. So various areas in field of computer vision, like you can talk about classification, where we demarcate different images. Object detection is one more thing, where let's say within a room, you have a picture and you want to say where does the electrical socket lies, where is a tube light, where is a fan, and all that stuff. That comes under object detection. Tracking is like when you have found out where the object is. If let's say if we are on a road and we are driving, tracking would locate the car which are front of us, and then it will help us detect where it has moved, whether it has gone back or forward. Retrieval is something similar where we are trying to figure out similar images based on X input image, or it can be a duplicate detection as well. So there are a lot of sub areas under image retrieval which comes. One more is OCR, where we are trying to decode what is there within the image in terms of text. They are more like face detections. So there are a lot of applications which are there. These are just few of them which we have listed. But these are the basic ones to get started. In all the computer vision areas, CNN is the main thing which plays a big role. We'll talk about this within a short while. Before going into any of these applications, we should first be able to understand what images are, what do they consist of, and how we can further use them for anything. So an image consists of, so let's say we say like this is 1080p image or a video. Basically, people are talking about the pixels which are there within that frame or that image. So pixel is like 1 cross 1 in terms of square boxes, where 1 pixel cross 1 pixel, 1 cross 1 is a box which is mainly describes about a single box. Like we can see on the right hand side here, we have got this box. So this is 1 pixel, which will talk about what is there within that pixel. So usually whenever we read images, we get some values in form of RGB. If it is a color image. Otherwise, we'll get a black and white, where there will be grayscale images between 0 to 1. We primarily use 2 libraries to read images. One is Opencv and Pillow, although there are more, but these are commonly used libraries or widely used libraries. The only difference between both of them is like they both read image in a way where the notations or the structuring of the values is a bit different, although they are both NumPy arrays. But in Opencv, first the blue color value comes in, then green, then red. In Palo, it is RGB, red, green, and blue. So only this small difference between both of them, but both of them play a big role for us to get started for image use, like for doing any operation with images. In any of our projects or in any of the computer vision areas, whenever we need to create data or we have some data, we may have to extrapolate the data to a larger scale so that image is easily able to understand the context from different angles, or different scenarios are covered within that whole data. So there, image augmentation plays a big role. So image augmentation is a technique where we increase our data set by applying some of the common operations. Some of those common operations can be enhanced. So enhanced means like either you are increasing the contrast of an image or the brightness, or you are applying some operation which makes the image much more clear than what it was before. Second could be a resizing, where like we are making an image small or big. That is mainly resizing. So this helps us to sometimes, like when we resize, it may be possible like the image may get blurry, like we see on the right hand side. So let's say if I just zoom this area out, then this may look something like this if we do it on a big scale. Zoom is one more thing where we are just focusing on a small part of the image and we are making it enlarged. Translation is something like where you have moved this whole image either to the right or to the left or to up or down. So let's say within this whole box, if I would move this area from here to something like here. So I'm moving from left to right here. So this would mean translation of the image. So this also adds, like, suppose if we are trying to do something and somehow half-baked image was given to us. So will the model be able to predict what it was and what it was not? That's where translation would help. In some cases, it may bias the model, but these are the things which we may have to deal with over time. One technique won't fit all the problems which we want to solve. Next is rotation, where like we are either rotating in a clockwise or an anti-clockwise direction, like both the directions would play a big role, like clockwise or anti-clockwise. So tilting the images or further smoothing them out are some of the common techniques which we use for handling the images before even doing anything for modeling. Moving to the next ones, in any of the computer vision task or any modeling, these are the basic things which we need. Without this, although we can do some of the stuff, but it may not be as efficient as we want it to be. So GPU is the basic component which we need to process image faster, although we can do it on CPU. But CPU would perform a lot slower, and sometimes we may see it getting blown out. Blown out means like it may get burned because of very high processing which is needed for processing images. Then whenever we do anything in terms of building models or predicting, CUDA and Sirian plays a backend role to do that stuff. These are basic requirements which we need there. You can also install them on the designated servers or machine which you have, or you can use some kind of Python environment which are linked with the, like we usually, what we do is we have got a couple of servers where we either install them parallelly or we get them clubbed under Python using conda environments to make them work. Now, when we talk about common frameworks which we use, they are TensorFlow, Keras, and PyTorch. We majorly use TensorFlow in our production applications. Rest we use for research purposes. But this may change over time as and when we see newer things coming out. In any of our project, this is the kind of life cycle, although people would have, like different people will have different notations of it. We have tried to make it a bit shorter, or let's say clubbed a lot of things under 4 buckets. So first is the analysis phase, where we try to see what kind of problem we are trying to solve, where we can find the data, how the data looks like. Then we try to find out what kind of important features would be needed for that problem solving. That problem can be related to classification or object detection or something else which we want to solve with images. Then once we are through with the collection of the data, analysis of that data, then we start building models. We try to research what works best with that data. And we also evaluate those models with some predefined metrics. They would change based on the algorithm, based on the problem we are trying to solve. And that would vary a lot. But for that, we need to understand basic ML matrices which are there. More or less, they are used in doing this stuff. Once we are through, like what kind of model works best for that scenario or for that project, we try to integrate that best model within the application, which anybody can see. After that integration, we just share it with the end user in terms of productionizing it, so that it can be used on a wider scale in any infrastructure, basically. But basically, we'll need a GPU there for hosting that application, because it would need a lot, either like we need to wait a lot of time to get the outputs done, or we can use GPU for a faster processing. So I'll just talk about neural networks here. This is a basic architecture where, so let's say when I was talking about kid trying to understand a single image based on what it, so let's say when I had a kid like 4 years back, start time when we showed him a dog who was there on the street, we told him this is a dog. But when he saw a monkey, he also said that monkey as a dog, because we never told my kid that this is a monkey, not dog. So my kid tried to say, because it looks something similar to dog, so it could be that. So unless until we share more and more data to, so how does my kid learn is like, so this is something like our eyes or brain, how it works is like some input comes along where to the input nodes where this data is taken in. They are processed to couple of hidden layers basically to get some kind of output in the end. Although these hidden layers can be 2, 3, 4, any numbers which you want. So the data gets percolated from each and every node. So these all circles which we see here, they're all nodes. So from each node, the values are passed on to the next node for further processing. And the output is the one which we need in the end based on that input thing which we get or which we see. So I think now Akshay will take over in describing some of the things.
Yeah. Thank you, Vaibhav. Hi all, I am Akshay and I'm a data scientist and I've been part of EX2 for almost 2 years now. So before we move forward, if you have any questions at any point, you can just ask us and we will try our best to solve your queries. Okay, so let's talk about some of the common terms that we come across in our neural networks, the network that just Vaibhav has just explained. Okay, so let's start with weights and biases. So weights are something which control the strength of connection between two nodes. Okay, so we transfer data from one node to another, and weights control or influence that transfer between that connection. And bias is something, a value that is being added to a product of weight and the input that is being given to a node. Okay, so let's move on to activation function. And activation function is basically a function associated with each node in a network which defines the output of that node. In simpler terms, when we compute the output of a particular node in a neural network, we multiply the input with weights, and then add bias. We use that entire mathematical formula and pass that to an activation function which decides the final output of a particular node. So these are the commonly used activation functions that we use in our neural networks.
Excuse me. Good morning, Akshay. I have just a simple doubt. I'm sorry, I'm actually intervening you now because I'll probably forget it. Okay, so you are talking about this activation function, right? So how you decide, can you sigmoid, ReLU, softmax, how you decide which activation function to use in which particular type of problem?
So I was coming on to that. Okay, so these are the basic activation functions that we use in our neural networks. Okay, so sigmoid and softmax are basically the activation functions that we use in the output layers. One is sigmoid is being used when we do the binary classification. It basically gives the probability that whether the output that we predict belongs to this class or the another class, while the softmax is being used for when we have n number of classification, when we have n number of classes, basically for a multi-class classification. Softmax divides the entire probability into n space, and the sum of that n space goes to 1. And the ReLU activation function we use, it's mostly used for the hidden layers, and it's not something that we use for the output layers. It's only used for the hidden layers. It basically tries to limit the output of each and every node. It computes the maximum of 0 and that node. So this is how we use the activation function in our projects.
Okay,
did I answer your question?
Yes, thank you. I mean, will you elaborate on ReLU? Because sigmoid is a very common activation function, probably used in logistic regression also. So
I can.
So can you just describe ReLU and softmax if it's possible?
Yeah. So ReLU works in a way we take the maximum of 0 and the W in weight into input plus bias. Basically, we limit our output of each and every node to the positive value or 0. We don't want our output of node to go below 0. We don't want that to go to negative direction. And softmax is simply a extrapolation. I would say extrapolation of a sigmoid activation function. It basically works for the n classes, and while the sigmoid works for the two classes, it basically works for the n classes. The formula remains the same, and it takes the input as it goes for the n number of classes.
Okay, do you have the equation like sigmoid function equation? I know. Do you have the function for equation for ReLU and softmax? How this function looks like?
Well, could you please write the equation for ReLU, like the
I'll
maximum?
maybe what I'll do is I'll just show it on the Google, like because these are very
Yeah.
common terms which we can see. So, this side should be good. So this is how it looks like.
Okay. Okay. Yeah. Okay. Got it.
And could you also show the ReLU? Maybe they are confused with the ReLU.
Pigment is this. Let me see if it is there. We thought we won't cover formulas here because it's
Yeah. So this is the ReLU. It goes with it takes basically maximum of 0 and the x. The x here is the output or the weight multiplied by inputs plus bias. So this is how the ReLU function works.
let's move forward.
Yeah. So next thing is this loss function. So as Vaibhav told, the neural network is trying to learn something that we give inputs to it, and it tries to learn what the input is. So it does that using a loss function. Loss function is can be referred as an objective function, which it tries to learn or basically minimize. Loss function basically computes the distance or error between the output of a neural network and the actual output. And how a neural network learns, it tries to minimize the value of this loss function. It basically tries to minimize the value of this error, and using this loss function it tries to learn. And learning rate is something which determines the step of our learning, that how big a step our model is going to take to update the weights or update the biases. And back propagation is an algorithm using which our model or a neural network learns. It is basically a way to propagate losses back to the network and update the weights and minimize the loss. Okay, so I think we have talked enough about the terms that we use in our new basic neural networks. Let's now move on to the building block of our computer vision application. So in earlier days, we were using only the fully connecting networks for the computer vision, and in recent years we have switched to CNNs, convolutional neural networks. They have improved our performance on computer vision application to a great extent, and they are outperforming all the fully connecting networks. Okay, so right here it's a basic CNN example. We are trying to predict the class of the we are trying to predict the digit that is being written here. It is an MNIST image. We are passing this MNIST image to a stack of convolution and pooling layers. I'll be explaining this convolution pooling layers in the next slide. And each stage we see that the dimension of the input image reduces, and in the last layer before the output layer, the image is basically flattened, or our feature is basically flattened and then fed to the output layer, which then determines the probability then determines the probability for each class. In the output layer, is written as the output layer determines the classes to which this image belongs. Okay, so now we can talk each and every block of that CNN in detail. So CNN basically consists of 3 layers. The first one is the convolutional, the second is pooling, and the third is fully collecting layer, as we saw in the previous slide. So CNN is based on the concept of convolution algorithm. Convolution tries to preserve the relationship between pixel values by learning image features using some kernels or filters. You can simply understand convolution as a mathematical operation which takes 2 inputs, first is the matrix or the image matrix, and the second is the kernel. So the leftmost matrix is the image matrix, and the middle matrix is the kernel or the filter that we apply on this matrix. So in convolution, we traverse the input image by passing on the passing filters, and we compute a single value for each filter that we pass on this image. As you can see in this slide, that there is a 3x3 filter which is passed to the which is traversed on the input image. It basically multiplies each and every digit and then sums them together and gives us back the single digit result. It goes on like this and produces a 3x3 matrix as the output, and this is what we call a convolution operation. Basically, we multiply the input image or the input matrix to a filter. We traverse that entire input matrix and we get the values. After the convolution, we go to the pooling layer. Pooling layer is nothing but what we use to reduce the dimensionality of the output matrix. So we will have the 3x3 output matrix after applying convolution, and what we do is we pool that entire output matrix to a single value, and we can do that by either taking the maximum of that and or by taking the average of that. And the last layer of the convolution network is the fully connected layer. Before feeding the output of convolution network, we flatten the output of convolutional layer, since our convolution output will be n by n matrix or m by n matrix. We flatten that and we pass that flattened array to a fully connected layers. Fully connected layer is simply just a feed forward layer that we use in our basic neural networks. Yeah, so I guess this is it for the common terms, and now where we'll be taking back.
Okay, so thanks, Akshay. So here, like you've seen like how CNN would look like in terms of basic operations. So whenever like we deal with any project or any problem which we want to solve, when we are trying to build that data, we usually try to build 3 sets of data to build robust models. So we divide the data into 3 parts: training, validation, and test. Training is mainly used for training the models. Validation is used to check each and every iteration. Like when the model is being trained, we check at each and every iteration whether how good the model is able to perform. Test is totally unknown data or unseen data, which is used to see how good the model is performing in the real world. So that data is never seen at any step during this whole training. Sometimes test set do give us a high level view whether our model is good to go or not. Although on the web, you will see people talking about just training and test. Validation becomes a part when we are trying to do the training of it, but we try to have these 3 data sets separate so that we can eventually see and differentiate between each and every iteration of the model training part. Let's say if we are doing training now, if we do it after 6 months or a year after, can we compare both the models? That's how like this is mainly used. Although if we talk about publicly available data sets, if we want to try out, you can go and fetch any of these data sets. So MNIST is mainly around digits, handwritten digits, which people have collected as a public source over a long period of time. Animals where they have collected images of different animals and tagged them up. CIFAR is mainly around 10 categories of data, like automobiles, cars. Smiles is mainly about different levels of variations of the smiles. ImageNet is a major data set, which I would say anybody within the field of data science would be using. This has been collected as like over a period of so many years, which I think is still being collected. And this has got millions of images across 1,000+ categories. And there are many more. So it depends on us, like based on our problem, what we want to do really, and which data set would help us to get started. But if we have to solve any custom problem, we'll have to build our own data set. For building, you can either like you first need to get raw data and then tag those data set or annotate those data across different taxonomy which you will create for your own projects. So let's say MNIST just created data sets across 10 taxonomy like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same goes for annual. So based on your problem, you need to define which would work best for your scenario and subsequently the data sets. But exploring them would give you a lot of perspective, like how you should be going about. So now let's look at if once we have collected the data set, what we usually do next to see or to look at how the training or modeling looks like. So here, like we are running this on one of our servers with GPU primarily. So here we have installed TensorFlow, and basically the version of TensorFlow is 2.4.1, which we are going to use for training and validating the models. So here, just the import, I assume like you have basic knowledge of Python, or you are able to understand what it is there. If you have any questions, you can ask us in between. Now moving to the next block, it says like we are going to process with GPU, but here we are limiting the uses of GPU to 0.5. If you do not want to do it, you can just leave it blank or you can comment it out. We wanted to do it in such a way like we can process multiple things parallelly. Here we are importing more libraries which will need for processing. We'll talk about this will come in just a while. So when Akshay was talking about CNN of on the basis of MNIST data, so that was one network. So if we want to train or if we want to build any network, you can do in like people basically do in two ways. One is they create their own network. So they define how many layers will there be, which layer will do what. So that's what they define. Here we have tried to showcase how the things are done via transfer learning. So transfer learning is mainly a technique where we take the inputs or from different models which are best in the industry out there, and we try to use them for our further learning of features based on the data set. So here we have tried to use Inception v3, which is based on the ImageNet dataset, and it's taking weight from that. If you want, you can move to any other. So there are lots of other techniques which or weights which you can use, but we prefer ImageNet to do this activity. Image size is one, like although like we know that there are lots of images out there, and every image has a different size in terms of height and width. Mainly in classification problem, people want or what we have seen is like 224 cross 224 resizing of images performs a lot better in terms of prediction, and a lot of noises are removed doing this. Although if you want, you can try with other image sizes, and you can compare which model does better in your scenarios. So we are saying that we'll take Inception v3, the image size will use something like this. This is 3 channels, they're like RGB. We are using ImageNet to load this model. So if you're doing it for the first time, it will load the model from the repository. This is one way. You can also do using TensorFlow Hub, like where you can download the model at your folder, and that's a different way of doing stuff, but it will give you something similar results. Here we are trying to load the model from Keras library or Keras bucket from TensorFlow. Moving to the next cell. So here what we do is like we say that we do not want to train based on the weights of the inception. We want to, so we remove the last layer from it, and we want to replace that with what kind of layer we have. So what we do is like mainly in the last layer, we have got those 1,000+ classes from ImageNet. We firstly remove them, and then we attach those layers with our layers, which are these 8. Here we have taken our data set. This is not full data set of ours. We have taken just few classes from the real estate industry. There are more like this, but we just wanted to have small set to show you how it works. Now, like Akshay was talking about the activation functions. So since we have got 8 classes, so Sigma won't work here. So we have to use softmax. So this is a multi-class problem. So we'll use this here. We'll pass on like this to further to the model for prediction. Here we have not trained the model so far. We have just loaded it, and we have just configured some of the attributes which we want as per our use case. Now, once these are inputted to the model, Sorry, any questions? So once we input this to the model, like before training, if you want to see how the model looks like, so you can see this model has got lots of layers. Some are convolutionals, some are max pooling. Then in the end, we'll see the fully connected layer, where the flattening of the output is basically done. So this is a pretty good network to start with, to train. Although if you want, you can train your own network as well. Now it comes to in terms of loss, like Akshay was talking about losses. Here we are trying to say we would use categorical cross entropy, just to say that we just want a single output for the input image. We don't want multiple outputs. Although whenever, like you will see on the web, people used to talk about top 1, top 3 accuracy. So if you want to do that, we can do it. But here we're just limited to top 1. Optimizers is this is mainly used for training. So we are going to use Adam, where it in the backend. It's a variation of stochastic gradient descent, and we have seen it works best in most of the scenarios. The metrics for evaluation, we would be using accuracy, like based on the input data set, how good it is able to predict on those data sets, like labeled one. Sorry, I forgot to mention one thing here. Like in computer vision, if we want, we can do anything in terms of supervised or unsupervised learning. The image classification, object detection, and OCR, they are majorly around supervised learning. Unsupervised would be mainly around clustering or similar techniques. And those techniques may have their own use cases. Here, since we have got these classes, so this is mainly supervised learning. So this was all about like model which we want to use for training. As of now, we haven't done anything yet. The next part would be like the model is there, but have we loaded the images? No. So how would we load it? So this is one of the methods to load the data set within the TensorFlow library. If you want, you can also load data set in form of a data frame and pass it on to TensorFlow to do it. There are multiple ways to do it. This is one of the easiest way to see. These are different techniques of data augmentation. If you want, we usually prefer to do data augmentation before this step when we are trying to collect the data set. If you want, you can do it at this stage, but it may take a longer time to process. So now, since we were talking about 3 data sets, training, test, and validate. So train is something like this. So what we are doing is we are taking, like, we want to take that folder where all these images are kept. We want to take all the images from that. The target size, if the images are not as per the size which we have mentioned earlier, if it is not according to that, just resize those images to this scale. Batch size is something like which, like, in a single iteration, how many images do we want to pick for modeling? Categorical is like since we have got 8 classes, so we are using categorical classification. So like there we had got bathroom, bedroom, elevations, and others. So that's why we use categorical here. What is a subset? You see, like in image generator, we mentioned that we want to have a validation split of 0.2. What this means is, let's say if we have got 100 images, 80 would go to training and 20 would be left for validation. That's why we have said, like, if when you are trying to generate the data from data gen, which we did above, just pick out the training data set from it and assign it to this. In similar fashion, we have done for validation. So please use these words carefully, because if you type something else, it may not work out. So our whole data set consisted of 76,000 images across those 8 classes. So this is what it is printed for the training. So out of the whole data set, 61K went to the training generator. Rest 20%, which is 15K, went to the validation one. Now, if we have to look in terms of,
I'm very sorry, I'm disturbing you.
Please.
Just one little doubt, like how you decide that how much % should go to validation set or how much % you go to train set?
So usually so there are some, I would say, golden rules. We keep on changing that. We usually keep it between the range of 0 to 20, not beyond. If you want, you can expand this to 20, 40. But if you expand it more, your training data would get a lot lesser and model may not be able to learn.
And I have one little doubt. You are talking about this validation, right? And what is the difference between this test set and validation, or they are same?
I'll show you, like, I'll just give me a sec. It will come within a couple of blocks in this notebook.
Sorry for intervention.
So here, like, if you want, you can do it 0.1, which will mean 10% of the data set. So this would further go down. Now, why we do it? It will just come within a couple of blocks. So we talked about those 8 classes. So whenever this data is fed in, although when the training is happening, they usually predict in some form of an array, which is something like this. Like this is 0 index in Python, 1, 2, 3. Just keep this in the back of your mind just for a while. I'll show you like where we'll need this to see what exactly these mean. Just give me a sec. It will be the last block within this whole notebook. So when we start training, we just say that we want to fit that model to this data set for training. Validation would be something like this. Epochs is the number of iterations we want to do. Once, like, within this whole block, what we have mentioned is, like, if we do not store the models at each and every epoch, only the last model will be stored as model and we'll be using it. If you want to do it, you can do it. But for that, you need to specify these checkpoints when to store. So which you can check out in the TensorFlow, like the documentation, how to do it. But if you do not do it, then the last epoch or the last iteration would be stored as is. Here we have mentioned, like, in each and every epoch, there are certain steps. So the calculation of the steps goes something like this. So I'll just show you, like, what is the calculation. So we have seen, like, in the training, we have got these many images. We say we want to do how many epochs? Sorry, we want to do 10 epochs. Epochs has nothing to do with the steps. It has mainly to do with the batch sizes. Sorry. So remember, like, we have mentioned this batch size of 32 in each and every step. So if we divide this both, so this will be 1932 as a round off figure. So in each and every epoch, it will be able to iterate over all the images if we go for these many steps in each epoch. Here, just for, like, I just ran it in the morning again for you guys to show, like, how it looks like. You can also remove it from here if you want. It will then train on these many epochs. I just did it by 2. So that's why you will see here, it is a division of 2 of 1932. Otherwise, like, this will run for more time. This I wanted to show you guys. So I just had it half. If you want, you can just have it removed and then train it. And if you want, you can also change it to 20. So these are all tuning which we need to do. Like Akshay was talking about learning rates. Here we have not dealt with learning rate because we are taking the same which are there in the Inception v3. So coming to the question, why we had got validation here. So let's say in each and every epoch, our model was getting trained. We were seeing the loss which was printed at the end of this step or the epoch. This accuracy is based on the training test set which was fed for that epoch. This is the validation loss. Like, that's why this validation comes in. So what happens is, each and every epoch, it keeps on checking how the model is training in terms of its validation on the validation data set. So this helps us to see, like, so there are 2 classic problems which we'll talk about in a while. Why we keep this. So you might have seen in machine learning, like, sometimes, especially with random forest, we may see accuracy close to 90%. But when you try to test it out on some data set, it sometimes performs really bad, maybe 5, 10, 20%. So when we feed it to something like this, what we are typically seeing is, like, on a training set, it is saying 80%. On the validation set, it's saying 87%. So we can say, like, the model is doing somewhat okay. If this number would happen somewhere around 20, then we would see, like, we would sense something is wrong with it. This just gives us some kind of view, initial view, like how this would look like. If it is going something wrong, then we'll just stop this iteration. We'll try to do hyperparameter tuning to further improvise the models or to further check whether the data is right or wrong. Sometimes there's a problem with the data, like the data collection has got mixed, like data is mixed across multiple categories. So the model is not able to learn when it is being trained. If you want to see this, so this is a classic way of seeing, but if you want to see it better, you can load up tensor boards, which will show you how this model was trained at each and every epoch or step in form of diagrams. Now, how it does for those diagrams? So before going to that diagram, so here, if you look at each and every epoch, so this is one epoch, second epoch, we'll see that the models was progressing a bit in terms of training accuracy. And so far it has went to 93.46 on training. And if we talk about val, it has gone to 90.32. Usually we vouch for 95 plus for the validation accuracy to test out on test data sets. Now, I was talking about those diagrams. So here, based on these runs, we have got like these training losses and val losses. We just try to plot it out like how it looks like. Logically, in every run, how would we want as the training or accuracy or the validation accuracy should go something like this. And validation or the training loss should go something like this. If we see a lot of variations around it, then we try to see what we sense that something is wrong with the model. So we need to correct it. So then we go around and test out why this model is behaving like that, either it's the data issue or the hyperparameter tuning or the learning rate was pretty high. Sometimes learning rate is so high, like the model is not able to learn and we skip the learning pretty fast. So these are common problems, which we'll talk about within the slides. It's there. So this is how the diagram looks like. Although if I would have just run it on the full data set, like not divided by 2, this diagram was pretty much clean. This time, like this val accuracy is somewhat hovering, but with that, like we usually prefer like the data should be it should be done on the full data set so that the model is able to learn a lot of stuff. And here also, like since we have taken a subset of our data set, this is just 61K. In ImageNet, we will see millions of images. So ideally, it is advocate like we should have lots of images so that the model is able to learn from different perspectives. Sometimes we may see a perspective is there within an image, so within the training set, but not in the test set. That's why the model perform sometimes bad, which is common across, not just in deep learning, in machine learning also we see similar problems. Now, once the model is like trained and we see, yes, the model is good, we just save it by this. So we use model.save. This is the name which you can give in any way, in any like normal feature which you want. I just named it like this. Now, once you have saved it, so let's say you want to use that model later on at some other stage. You just need to use these two. Like first, this is for model loading. You don't have to have the whole thing before this. So we just load the model. Now let's test it out. So this test image, which we were talking about, this is not from our training or validation set. We were just testing it out to show like how it works out. This is not a whole test set. Usually test set is similar as validation set in terms of numbers, and which has never been seen by the model, be it training or be it val. So when we run this whole thing, so this is how the NumPy array looks like of an image, which is loaded by a TensorFlow method, like load image of it. And we are saying like we want to resize that image to, or we want to have a target size of this, so that the thing which we have trained on, like since we have trained on 224 cos of 24, the same is done at the prediction stage. So this is mainly a prediction stage. We are trying to predict what an image is. So here we are just pre-processing that image before predicting that image to the model. So once we have passed on that image data to that model, the model has given something like this. Now, how to interpret this? So remember, I was talking about some class indices on the top, like in the middle portion of this whole notebook. So this 0 means, so this is 0, this is 1, this is 2, this is 3. Or you can also have it in some way like the names of this. If you will see these are arranged in alphabetical order. So the same is used here. So since we see in this whole array, the 0th index has got one, which is like, this is the one which model has predicted. And if you look at the 0 index, this is bathroom. And this is the actual image which we predicted. So we can say like, yes, this looks right. Now, if you want to do it across similar images, we just have to load all the images, predict it, and just validate it like what it really is. So this is how we train, save, and test out the images within this whole ecosystem. So this is one way of doing stuff. There are a lot of other ways, but this is a classic way for you to explore. If you do not have GPU, you can also use Colab. Like there are 3 versions of it, free, like, and 2 paid versions. So based on what you prefer, you can try out with that. If you have GPUs, then I think the way to go forward is the CUDA and the Resizing in the first requirements, and then Python specific versions. Either you do it with the base Python or you do it with the Conda, or whatever you prefer. We prefer Conda to do it because there are a lot of handling of libraries done by it. So this was a bit about classification. I will just ask Anurag to talk about the next ones.
Thank you, Vaibhav. So I'll just talk about object detection a little bit. So the main problem statement of object detection is like detecting where a object is in a given image. So saying where the image is giving the bounding box as an output, and also saying what object that is. So as you can see in this example, maybe say a human. So we point out where the human is, and then also say that this bounding box is pointing to a human. So this is the problem statement of object detection. So we will also look into a little bit in the general architecture that is used, and then we will also see a notebook where we can train models. So here, as Akshay and Vaibhav was mentioning, so the basic backbone is like a CNN and pooling, and again fully connected layers. So a variation of that only. So the things are just arranged a little bit in the way to solve the object detection problem. So the image is firstly fed into a CNN. So it generates like the features that we need. So these features are then given to a region proposal network. So this region proposal network, again, it gives out it tries to predict a very preliminary bounding box kind of thing. And also the raw features also. These things are then go to this region of interest, pulling and that like consolidates the results, and then feeds it to common. When I say common, I'll come back to it. So a common fully connected layer block. So this common block, and then this common block is again split it into 2 parts. So as intuitively we can think that when we see an image, we firstly we will just point to the object, and then maybe we say where the object is. So we'll first find it to be a human, and then like say where the human is. So similarly, the model also like breaks the thing into 2 parts. So where the human is, and it's a human, so predicting is it as a human, as opposed to like other objects like in the previous images, say building. So this bounding box belongs to a building, this bounding box belongs to a human, and similar things like that. So there may be many objects similar to that. So this is the overall architecture of object detection. So this is a single shot detection model, and it trains on like a little like smaller data sets. Maybe if we have like smaller data sets, we can still train it and get some good results. So yes, I'll just share my screen then, and then I'll go to the notebook maybe.
So there are multiple architectures. SSD is one of them, which Anurag is
Yes.
going to show.
So for this, as the format is pretty similar to what Vaibhav showed for classification. So we are also using a transfer learning method. So in transfer learning, what we do is we take a pre-trained model and then use that notion of that model to like further fine tune it on our data set. So on our problem. So the first thing what we are doing is we are setting the libraries here. So the first thing is getting the TensorFlow models from the TensorFlow GitHub repository. So that is what we are doing here in the first cell. So we are cloning the TensorFlow models uh, repository, and we will use it here when we use the object detection API and object utils and visualization and other stuffs from there. So this is the first part. Then we come to this part where we install the downloaded repository. And thirdly, what we do in this third cell is we get the weights that we want to restore in the model. So the first part is like in the setup that I mentioned, we will get the uh, architecture of the model. So we'll get the structure of the model, and we download the weights separately, and then we'll load that weights in that. When I say weights, mainly think of it as the knowledge of maybe this ResNet 50. There's this ResNet 50 weights that is the knowledge, the previous knowledge that we load into the model, and then we tell the model that to get fine tuned in the data set that we will be using. Here we are like importing libraries similar to the last problem in this part mainly, and we are using the object detection API that we just set up. In this cell, we have pretty basic functions. The first one being loading the image into NumPy arrays. So we use Google's TensorFlow input-output library as opposed to like Pillow and Opencv. We can also use Pillow and Opencv and then convert it to NumPy. Similar stuff. The second function will be like to visualize the detections. So whenever we either we visualize the image or our image with the bounding boxes and the labels. So this function we use for that. So we have this pretty simple data which we get with TensorFlow, and the data kind of looks like this. It has this rubber ducky as the object that we will detect. So we have this just 5 images. So we'll train on this only these 5 images, and then predict some unseen images maybe. So the first thing to do we after visualizing this data is getting the labels. So we'll have to since also Akshay and Vaibhav mentioned these are supervised learning problems. So we need to tell where the objects are. So where the objects are, and also what objects they are. So here category index gives us the list of the objects that we have. So here we just have one object. It's the ducky, and its ID is 1. So when I say ID is 1, so our object so in any object detection problem always has a object that is called background. So background will be 0th index, and that is not mentioned here. So that is understood by the model architecture as is, and we just mention it from the first index, the first index being the key. And then yeah, the data set being small, I like tag the data manually, but you can also you will have to like tag it using some tool. For our internal purposes, we use a tool called email label img. So you will have to then it's a UI based tool where you tag where the images are and where the objects are and what objects they are, and then convert it to the same format. The format here is like normalized with width and height. So we get y mean of the bounding box, then x mean, then y max, uh, uh, and x max of it, and we also like normalize it with the width and the height. So keeping it like from 0 to 1. GT labels gives us the like the object IDs here. So when I say these are the five NP arrays, and each array represents the object list for the first and the second and third and the respective images. So this first array is of index 1, and index 1 is again the key. So if you have like multiple indexes here, so if you have multiple objects here, then you maybe this can be 1 and 2, and then maybe again 1 and something like that, and you will get the object there. So this is a basic data set that you need to prepare before training. So once this is done, so once maybe you like tag it with label ing or some similar tool, then convert it to this format. Then we will be converting this data set that we created into training that training tensors that we will feed to the network to train. So that is done here. So we prepare the tensors here, and once that is done, we visualize the final data set. So we again we are using that plot detection function that we wrote like previously, and we see that we have tagged the same images here, and we say that this is the bounding box of the first image, and here the ducky is, and same for this one, same for all the 5 images. I went through this model architecture previously, and yes, the similar architecture is used for training here. In this section, we are loading the models as like I said, both the architecture we are loading the architecture from this config file, and then after loading that, we are loading the checkpoint like the weights in the architecture. So we are after doing that, we are prepared with the model. One thing that I will mention here, because the ResNet model has never seen a ducky image, so it will be foolish of us to like train like use its previous knowledge for this classification part. So we are not using it for the classification part. So we are retraining this part from scratch, and that is why we are like commenting out this part, and we are not using that. We are just using the box predictor part, so where it gives us the regression like array of the box that it tries to predict. So once that is done, we start the training. So we said that this is the learning phase, and similar to the last classification problem, here we have the batch size. We have set it to 4, so we just have 5 images, so we can set it to a small number. Maybe with larger data set, you can set it to a greater number, but as you set it to a greater number, you would be needing more memory in the GPU, and if and also processing power. So we set the learning rate to be pretty small. So we want it to learn pretty easy, like in small steps, and then we have this number of batches as uh, like when I said number of batches, it's just like the number of epochs that Vaibhav was mentioning. So it is the number of steps that we will take to learn. So yes. So in each step, we just take four images. We are like training these parts only. So the trainable, we are taking the trainable variables, and we are just training these 2 parts, where we have this convolution box set where we predict the boxes, and convolution class set where we predict what class that box is. So mainly maybe where the ducky is this first part, and that it is a ducky is second part. So we get it in this trainable from this trainable variable, and then we put it in a part. So this is the main train step function that we are writing. We will be using this to train the model. I'll go quickly through it, and if you have any like question, you can ask. So it gives us a good idea about the whole process that Akshay was mentioning, and Vaibhav was mentioning, that back propagation and kind of stuff like that. You can see that so we take the input size. So in the input size, in this case is 640 into 640, and then 3 is for that RGB channels. So the three channels. So we provide the ground truth being the tagging that we just did. So we provide the boxes and the classes to the model. We have this part where we just pre-process the images and stuff. Here you can see that like the loaded knowledge that it has, and no fine tuning as of now. So it tries to predict some output, and maybe this output will not be as we desire for our data set, but it tries to predict this part. And then as we were mentioning, we compute a loss here. So the loss is mainly the difference between the actual ground truth which we tagged, and the thing the model predicted in this step. So there will be some difference in the initial steps. So we hope that as the training goes on, this difference will be lesser and lesser, and eventually maybe just the same, so that the model will learn the whole thing. So we do this. So after prediction of this loss, so we have this two losses. As I was mentioning, we are training these two parts of the network. So we have this first localization loss for the bounding boxes. So it's a regression problem, and then this classification loss, and we take the total loss. After this total loss is taken, we get the gradients. Gradients are nothing but how much we want to change the weights and biases. So after the loss has been computed, how much we want to nudge the weights and biases to get to a better learning stage, maybe. So we compute that gradients and apply that gradients. So once the gradients are applied, in the next step, the losses will be lesser, and it goes on, so in a loop. So here we are using stochastic gradient descent as optimizer, and the learning rate being 0.01, and the momentum of the change of the learning rate is 0.9 here. You can nudge these are hyperparameters, and you can nudge them as per your need, and you can train multiple models and then see which one does better. So here the fine tuning starts, and then we shuffle the take the training samples, and we take some of them as per best size, like 4 or 5, and any 4 or 5. So it's a pretty small data set, but as the data set goes larger, then this shuffle part helps a lot. Then we use this train step function, and we also take this total loss of each step just to print it out. So once the training starts, you can see that you will get this is batch 0 out of 10, and the total loss after that step was this much. As you can see, the loss gradually decreased and decreased. So that is what we desired. Once that is done, we go on to this part where we take test images, and then run it on the model. We have this detect function here, so which does similar stuff like prediction, and then post process something. So then the post process gives us this uh, detection boxes and detection classes, and also detection scores. So we also have this how sure the model is about this being a ducky, and where the ducky is. So that is in the detection score. So we use that plot detection function that we wrote, and we have these images which the model is not trained on, but once we feed it, we also say it's intelligent enough just not to like demarcate this as a ducky, but also its reflection, because it like says that yes, this is similar. Although you can see that the viewpoint of this first image and this second image is like pretty different, but still it catches that these are the things. So yes, that will be all in the notebook. Maybe I can Vaibhav, you can share your screen and we can talk a little bit about the challenges maybe.
Sure. Is my screen up?
Yes, just give me a sec. Yes. So there are some common challenges in both image classification and OD, and maybe in or like in, in whole of computer vision maybe. But the first one being intra-class variation. So as we just saw, there may be some in some examples in the training set where we try to the model tries to like get a notion of the object, and maybe the variation of that thing is like completely different in the test set. So maybe uh, its color is different, it's like shape may be different, maybe the dog seem like something in the training set. So and we get like a bizarre dog from somewhere in the test set, and we cannot identify it as a dog. So that happens. Then comes this viewpoint variation. This is also a variation part where maybe just as we were discussing, maybe some object we see it from different viewpoints, and then some viewpoints are missing from the training data set, and the model did not learn about it, and it fails in the test data set. Occlusion would be a thing where maybe the model faces some obstruction and something like that in front of the object. So maybe the object is not totally like invisible, but there may be some object in front of it, or maybe the salient like the focus maybe not on the detected object. Maybe there are many things, and then there may be a small object that we want to detect. So that can be a problem in occlusion. Blurriness and noisiness, and these two are like if the image is of like if it's not very clear, so it's blurry, then the object the model will fail, surely fail. But maybe it will try to do something like that, but the kind of confidence score of will be lesser. Noisiness is in the similar lines, but maybe the resolution is lesser, or maybe the contrast and something like that is out of like what we want it to be. So the model can be like predicting wrong things there. And then there is this class imbalance. Class imbalance is a thing like in both in maybe in classification and OD. If we have this same number of examples for all the classes, then the model learns best. So if we have like a lot number of images for us one class, and then maybe like very less number of images for the other class, then the class the model will be very much biased to that the class that has the larger number of images. So that we don't want to happen. So generally what we do is we augment data, and then we try to try to somehow we try to like equalize all the classes, either by like replication or like augmentation, or like decreasing the data in the larger set. Here we have this yes, we here we have this third part where we see a problem. If the model either gets underfitted, so the all the examples that it is getting in the training set, it doesn't catch the whole notion of it, so it gets underfitted, or else it gets very attached to the training set. So it like really goes into the training set, and it overfits on the training set, but it doesn't generalize. So then if it's overfitted, then it will go and perform very badly in the test data set in the outer world. So the best thing to do is get a balanced training, then the model generalizes, and it can both work good on the training set and also most importantly on the test set. So yes, that are the challenges in this computer vision problems. So maybe I'll that will be all from my side. I'll ask Akshay to take it over and talk about OCR.
Yeah. Thank you, Anurag. Hi again. So I'll be taking you to OCR journey, and let's just dive into it. Okay, so OCR, this will be our last use case for today that we are going to discuss. It stands for optical character recognition, and it is defined as the process of extracting text from digital images. As shown in this image, we are trying to extract "Hello World" that is written on a paper. And in today's world of OCR is used in various places. Vaibhav, could you please move forward? So in the finance sector or the banking sector, we are using OCR to process bank checks, to digitize that check processing, and to store that information in electronic form. And we are also using OCR in daily life. We can see the example of OCR in the number plate recognition that is being used by the government for the traffic violators. And we use OCR can be used for the recognition of handwriting, basically a text written by someone. We can use OCR to predict that text, or convert that text into an electronic form for storing it for the longer duration. And nowadays many postal services are also using OCR. They use OCR to extract the addresses and from the packages, and trying to automate the entire delivery process. Okay, so let's talk about some libraries that are open source and that we use for doing OCR. So there are major three libraries: Tesseract, EasyOCR, and Keras OCR. These all three are open source, and now we will show you an example of Tesseract and EasyOCR. Okay, so this is a notebook. This is a Jupyter notebook that will give you an idea that how do we use Tesseract and open source and EasyOCR. This is divided into two parts. First, we'll discuss Tesseract, and second, we will discuss EasyOCR. So Tesseract is an OCR engine that you can easily install on your system, and you can use it via command line, and you can use it using Python APIs. So using Tesseract engine by Python APIs, we have a library which is called PyTesseract. It is an open source library. It interacts with the Tesseract engine. So the first step would be to import this library, and then the second step would be to set the path where we have installed our Tesseract engine. So we tell our PyTesseract that this is the path from where you need to extract, or where the Tesseract engine is installed, and you interact with that. And the next part is we'll just simply see the image that we are going to see, that we are going to perform OCR on. And the next step is very simple. We can simply perform an OCR on this image by a single method. We use that image to string method in the image on the image itself, and it gives us the text that it was able to predict. We can see that the text that we predicted is not very accurate, and it missed a lot of text. And since you can see that there is a lot of text in the image that is being written, but the Tesseract was not able to correctly predict all of that. So this is basically because the OCR is not like very simple. We cannot just simply give in the image and get the text back. We have to do some kind of pre-processing, and sometimes we have to tell the Tesseract engine that these are the specific regions, and these are the regions where you need to look out for the text. And based on those pre-processing steps, only then Tesseract will be able to enhance its performance. Okay, so those steps could take a different other different lecture. So we are skipping that for now, and we are just jumping to easy OCR for now. So easy OCR works in a similar way. Okay, so we just it is an open source Python package that can be installed via pip install, and we just import it and then specify the language that we're trying to predict. In the step that we in this step that Vaibhav is trying to show, that we are setting the language for our OCR. In this case, we are trying to predict English language, and that is being represented by en in easy OCR. And the next step is very similar. We just use another method, different method as per the library, and we just predict the text. So there is this reader.read text, which we pass in the image path. Here the not the entire image is passed. Here the path of the image is passed. Okay, and we just get back the result. So there is a parameter in this which tells us that the result is in the form of the bounding box and the text that it predicted. So the bounding box is basically the box that bounding box is basically the region where it predicted that text, and then it returned that text. So it ran with the default configuration in which it returned bounding boxes as well as the text. So if we change a parameter to there is a parameter which we call as detail. If we change this parameter to 0, then it will only return us the text and not the bounding boxes. So this is how you can use OCR. And what we do in our company is we first do the object detection on the images that we get. We try to find out the regions of interest, and we pre-process the regions of interest. We try to enhance their quality, and then we pass them to TestDirect or easy OCR engine. And then we post-process the text. Basically, we clean the text, and we do some kind of spelling correction and all. So that is the entire pipeline that we use in industries. But to start with, you can just start with you can just plug and play with these two libraries. Okay, so now there are some challenges that is someone trying to ask any question? Okay, so now there are some challenges that we face. These challenges are similar to what we face in other computer vision applications. So the blurry image challenges will always be there. No matter what, if we get images which are blurry, our performance goes down, and OCR pipeline basically fails if it gets blurry images. And there is an issue of inconsistent font and inconsistent handwritings, and we have infinite number of fonts and infinite number of handwriting variations that we are not possibly able to configure a TestDirect pipeline for. And then there could be different orientations of text. Basically, the text could be aligned at a different angle, and how our open source libraries are meant to work. They are meant to work with only the horizontal alignment of text. So we will have to realign the text region to an horizontal text, and then pass it to our TestDirect, and then pass it to our OCR engines. And then there could be overlays. That basically a overlapping of text on text, and this is still a challenge that we are not able to solve as per the current resources in the market. So these are the major challenges that we face in the OCR. Okay,
So if you want, like you can also train your own OCR engine based on MNIST data or something else, where you can decode or you can build models which will predict what the text is. Here we have tried to use open source libraries for like what OD, like Anurag and Akshay were talking about. So we use something like this library to do it. If you also want to do it, you can do it in this way, especially for OD. For others, there are different libraries for collect the data. Okay. Sorry, Akshay.
Yeah, so that was pretty much it from our workshop, and you can ask your question or shoot your questions at us, and we'll try to resolve as much queries as possible.
Any questions? Although we know like this is too much stuff.
Any question from the participants? Yes, Dr. Parveen, any questions?
I just have one small query. you were talking about there is a problem with overfitting and underfitting. So do you have any explicit method to solve that problem, or it's like
So
this?
first you need to decide, like we need to check whether it's an underfit or an overfit.
Okay.
So we can say like random forest mostly will mostly overfits. If we are like, if we train too much, like too many epochs, and like the thing which we are talking about in terms of, I'll just draw it out here. When we were talking about that accuracy and the loss, if the accuracy is not going up and you are further training out for more and more epochs, this will surely go in overfit state. Or sometimes your data is imbalanced, then surely underfit. Like so these are common things which we try to decode with the help of diagrams, like how our training and validation loss are working out.
So basically, you have to monitor your process, your validation and training loss all the time. And if at any time your validation,
I can totally understand why underfitting is bad, but I have little confusion why overfitting is actually bad.
So overfitting would be bad. So let's say your model has learned a lot more. Whenever you try to give a new dataset which was never seen, it may say something which you do not want it to do.
Yes,
Okay.
Arushi.
So treat overfitting as we are overfitting here the training data. Okay. So we are able to get all the training data right. Okay. But when it goes to production, when it goes to the real life images or real life data, it's not able to perform well. So that's overfitting. Basically, when our training performance is very high, but our test performance is very low. The performance on the data that it has not seen. So that is why the overfitting is a problem.
Okay, so you mean to say our model should be a general model which should work on test set, and because if you overfit it, it means you are actually making the model very
Yes.
specialized.
Yes. So basically, we're trying to build a model that can be used in real life applications. So we in the real life application, there could be variation and there could be any kind of data. So we don't want our model to give wrong predictions on the real life data. Okay, so that is why we don't want our model to learn only just the training set. We want it to be the generalized, and that can be extrapolated to other problems or the real life problem actually.
One of the methods which I have learned of overfitting is about regularization. So I don't know about CNN much as well as OCR. So the idea of regularization works there.
So yes, so you can use regulation here as well. So there are lots of techniques to do it, not just balancing the data. So you can use regulation in this whole ecosystem as well.
one of the common technique is dropout. When you have long and deep neural networks, you usually embed a few dropout layers within those network.
Thank you very much.
So there
So
is a
those,
question from Arushi Sharma on chat. Okay, so yes, we can do that. I think Anurag will be able to answer that question in a much better way.
Yes, I was just writing that. So you can use the object detection model for this. So the object being the crack, and you will also get the like the exact position in the image where the like the crack is, and you can also do it on like just to like mention, you can also do it on videos. So videos being collection of frames, so you can detect where like crack is in each frame, and then get the results. So yes, you can train an object detection model for that.
but your images should be of high quality. There should not be any noises around it, because let's say if in the old houses, sometimes we have cracks. In some regions we do not have cracks, but there are dust or pollution like which gets stick to the walls. So it may also detect them as cracks. So you need to really demarcate between both of them, or your images should be a lot clearer.
And you should also focus on pre-processing, and I guess for this task, using some kind of a binary image would do better.
Mhm.
Yes, any other question from the participants? So anyway, thank you, Vaibhav sir. It's very, very, enriching our experience, especially how to have a, a real-time project development, especially the image processing. And second thing, I would like to share that it's your team effort. Despite having Vaibhav sir having the COVID, it's a team effort, and which reflect the working style of an organization. That's really, really appreciate.
Thanks, Dr. Anand, for the opportunity. Like this is like you said, it's a team effort. We usually help each other out in any scenario, and that's a good part which is there in the industry, and that we have learned especially from our colleges, like friends being friends. So thanks
Yes.
for the opportunity for giving us this opportunity to share things which you have learned, so that it can be further percolated to others.
Thank you, the Anurag sir, Vaibhav sir, Akshay sir, Kashif sir. It's really, really, really enjoying that is showing you that efforts to present this, faculty development program, especially in the computer vision. And I would like to ask something about the green building concept. Since you have very rich experience in the real estate and the image recognition, is there any organization which is implementing the green building concept?
What is green building concept?
Means the green technology, especially the various power sources being consumed by the big IT buildings. And
so Dr. Anand, like our industry is real estate, especially in building new homes for consumers. So their homes are usually energy efficient, and they are mainly in the US. So although the homes from outside, they may not look as an energy efficient, but there are installations which are done within the houses, and there are lots of other things which we cannot see when the home is built. Yeah, but when the home is in the building state, like under construction, then you can check them out, and those images can help us to say whether this image is a green image or not. In terms of like, if you're talking in terms of the glasses, then I think we need some expert who deals in the glasses, like which glass is of green type and which not. Like those kind of expertise is needed to answer that question specifically.
I'm just inquiring that with the new building bylaws coming up, especially the Godrej homes, they are coming up in Faridabad zone and other areas, even also in the real estates. So they might be using this new concept of, and especially using the machine learning concept.
Surely they would be using it to tell like which is not and which is green and which is not, or which is more efficient or not. So it all depends on use cases. Like we had got image classification, OD and OCR 3 use cases. There are lots of use cases for which specific data sets needs to build out. Let's say in your case, that in your problem, which building is green, which not, or levels of greens, that data needs to be collected for the model to build out.
So thanks a lot for such a, giving the meaningful information, especially the computer vision, and that to a real-time project and applications that your company is going on in the real estate. So thanks a lot, and thanks for the team also. Thanks from the Akal University.
Thank you, Dr. Anand. Thanks, Akal
Thank
University,
you.
for
Thank you.
giving us the opportunity.
Thank you.
We are winding up the session, participants, and we'll get back to you soon in around at 2 p.m. So right now we are winding the session. Thank you everybody.
Thank you, everyone.
Thank you. Bye.
Thank you, everyone. Bye.